You may begin to complain that the method introduced in Lecture 49 is too mathematical. The glamour of circuit analysis is liberating us from complicated mathematical analysis and letting us view the process of the whole circuit from the viewpoint of physics. Three-element method, which will be introduced in this lecture, is a vivid example. Let's start. The three elements are three numerical quantities. You will find after having these three numerical quantities, we don't need to list the equation and can find a solution for any branch variables. And more importantly, we can solve the three numerical quantities by analyzing the resistive circuits. Firstly, let's review. In last lecture, we used the classical method for first-order circuits to analyze these two circuits. One is a serial connection of voltage source, resistor, and capacitor. Another is a serial connection of voltage source, resistor, and inductor. We solved the UC by listing ODE and finding 0 plus. This is the solution, and this is about UR. For the second circuit, we list the equation, find 0 plus value. This is the solution. In the last part of the last lecture, we've analyzed the natural response or general solution and find if RLC are all positive. The time constant for first order is greater than 0. So natural response or general solution elapses with the time. Finding the special solution of differential equation is equal to finding the steady-state solution. Now we draw the three branch variables waveforms. The yellow curve represents UR. The red curve represents UC. And the brown curve represents I. We can see for the 0 plus value, we can use switching law to solve, which is introduced in lecture 48. For the change speed of transient process, we can use tau equals RC or L over R to solve. For steady-state solution, we can analyze a steady-state resistive circuit. For this steady-state circuit is like this. In other words, when the excitation is DC source, the capacitor is open circuit long after switching. For this, the steady-state circuit is like this. In other words, when the excitation is DC source, the inductor is short circuit long after switching. We can get all steady-state solution by solving resistive circuits. For any branch variables, we can get its expression after solving its initial value, changing speed, and steady-state value. This is the main content of this lecture. The method discussed in this lecture is the most important method for solving first-order circuit. Now we do some derivation. This is the first-order linear ODE with constant coefficients. Suppose A is greater than 0. As a simple case, we suppose X, that is the excitation, is a constant. Our analysis is similar to that of the classical method in last lecture. Its characteristic equation is lambda plus A equals to 0. The characteristic root lambda equals minus A. So the homogeneous general solution is A times e to the power minus A multiplied t. We still need to find one special solution of inhomogeneous equation. For constant excitation, we suppose U double prime is the constant y, and dw prime over dt equals 0. Then the differential equation is written as A times y equal y. So y equals x over A. Then we know U double prime equals x over A. The general solution is U equals I over A plus A multiply e to the power minus A times t. This is the contents of the last lecture. In the previous page, we've discussed if A is greater than 0, this part elapses with the time and tends to 0. Suppose this part is a steady-state value, which can be written as U infinite. Then the solution can be written as U infinite plus A multiply e to the power minus A multiply t. For RC circuit, A equals to 1 over RC. For LR circuit, A equals R over L. So the solution U equals U infinite plus A multiply e to the power minus t over tau. This expression is the same as this expression. Our view is changed from mathematics to circuits. The undetermined coefficient A can be solved with 0 plus value. In other words, U0 plus equals U infinite plus A. Because this part equals 1 when t equals 0. So we can find A equals U0 plus minus U infinite. The branch variable equals U infinite plus U0 plus minus U infinite multiply e to the power minus t over tau. Now we completed the circuit analysis. Let's see. U represents any branch variable, such as a voltage or current, with 0 plus value, steady state value, and time constant. We can use this to get any branch variable's time domain expression. Now we make the equation more complicated. The excitation part of differential equation is not always a constant. That is, circuit excitation is not always a DC source. It can be sinusoidal signal in the following discussion. In this condition, our derivation is similar to the above. The only difference is U infinite is a function with variable t. Similarly, U equals U infinite with t plus A multiply e to the power minus t over tau. U0 plus equals the 0 plus value of U infinite plus A. So A equals U0 plus minus U infinite 0 plus. The branch variable equals U infinite t plus U0 plus minus U infinite 0 plus. Multiply e to the power minus t over tau. By comparing, you will find their essence are the same. When the excitation is DC, U infinite is a constant. When the excitation is a time function such as a sinusoid, U infinite is a function with t. Once we get the steady-state solution with a sinusoidal excitation, we can also easily get the time domain expression of the first-order circuit. You must remember these two expressions. It's not hard. We can remember it from two aspects. Firstly, this part equals 1 when t equals 0. So the sum of all these parts must be U0 plus. Secondly, this part equals 0 when t tends to infinite. So this part must be steady-state value. It's easy to remember the expression with these 2 points. Finally, you should notice that steady-state value, 0 plus value, and time constant is the 3 elements of solving first-order circuits.